In particular, can anyone give me a kind of a succinct description? What causes a loop? I mean, how do we get into a loop? Or once we're in a loop, why are we in a loop? I think someone said something very similar to this earlier. Yes. Roger. Yes. So I think you're answering the question of, hey, how do we stay in this loop? And even mechanically back and forth, why do we accept updates? All very true. I was looking for even more broadly, a direct loop means that I think that I should give my packet to you, and you think that you should give your packet to me. So we have forwarding tables that kind of point at each other. That's very unfortunate. And so how do we actually get into this scenario? Well, imagine you have a network like this. And here, this is all valid forwarding state where to get to D, R3 thinks I need to give my packet to R2. To get to D, R2 thinks I need to give my packet to R1. And R1 is directly connected to D, so this will work. But we run into an issue where if a link goes down, well, eventually, R2 is no longer getting updates from R1. And so its entry is going to time out. But R3 is going to advertise saying it has a path to destination. That advertisement comes in, and R2 is pretty happy about that because it no longer has any way to get to D, and so it's very happy to hear that R3 does have some sort of way to get to D. So great, R2 accepts that, says my next hop is R3, the path of cost of 4, which was the cost of R3 plus the one hop cost to get to R3. And unfortunately, this is just going to go on back and forth. They're going to keep passing these updates to each other and updating the costs, counting all the way up to infinity. So I get to 6, to 7, to 8, and this continues forever. Okay, now finally we can get to talking about what the confusing parts were for routing for me. Specifically, this is the class of problem, or at least how I think about it, of what split horizon and poison reverse are attempting to solve. We're trying to prevent loops from happening. And if they do come up, making sure that we get rid of them as quickly as possible. So split horizon comes in, and the rule with split horizon says, if I have a route through you, I will not tell you about my path. I will not tell you about that route. Because why would I ever tell you about a route that goes through you? If I tell you about it, you shouldn't ever have to use it. If you do have to use it, we're in a loop. Because if you give me a packet, I'm going to give it right back to you. And this sounds pretty good. I mean, in fact, if we walk through what happens here, same link goes down, same forwarding table entry times out, but then D is just not going to say anything. Sorry, R3 is not going to say anything to R2 about its path to D. And so eventually, R3's path times out, sorry. And now we're in a state where neither R2 nor R3 has a route to D, and hopefully someone else in the network sends an update to R2 or R3 saying they have a path to D. And at that point, we can accept that new path, and our network can reconverge. Hopefully, that's what happens. Does this work? Yes, everything works sometimes, yeah. It's a safe answer. Does anyone have a more opinionated answer? I mean, I think it works. It should work, yeah, ideally. So it does work in the sense that you can't really have a direct loop form in this case. But there are still edge cases where you do get loops, direct loops forming. You saw one in a previous lecture that Murphy did, where there were two routers talking to each other that had a path through some third router. They both went through the third router. When that third router went down, if a timing comes out just right, where R1 and R2 tell each other about their paths through that other router, and the routing entries expire at the same time, you can get into a state where they are now sending packets to each other again. So there is this edge case, and you'll see it very closely on the project. And so split horizon works to prevent many kinds of direct loops, but there are still edge cases where they can come up. And what happens in those edge cases? So let's say that with one of these edge cases, we get into this scenario where R2 wants to give its packet to R3 wants to give it to R2. Split horizon does get us out of this issue where R2 is not going to tell R3 about its route, and R3 is not going to tell R2 about its route anymore, now that they're pointing at one another. And so eventually, the two entries time out. But we have to wait an entire time to live. So the entries actually have to time out. And remember, TTLs are like usually considerably greater than advertisement time. And so we're in a loop for a little bit of time. So this is where poison reverse comes in as an optimization. So it's an improvement on split horizon. And it says, actually, instead of just being silent about my path through you, I'm going to actively tell you that I have an infinite cost path. Okay? So if I'm going to route through you, I'm going to tell you I have an infinite cost path. And often you'll hear this talked about as lying. Why is this conceptually lying? Because you do actually have a path that is less than infinite cost, but you're going to say it's infinite cost to make sure that in no world is your neighbor going to give you a packet. Yeah? And all routers, like, who's going to send a packet on a path with cost infinity? And so what happens is, assuming we somehow got into this state, you can trust me that there are these edge cases you'll see on the project. Once we're in this kind of looping state, if D is going to R3 is going to send an update to R2 saying that its cost to D is infinity, and R2 has to accept that, by the way, right? Someone pointed this out earlier. You might wonder, well, whoops. Well, why is R3 going to accept a path with cost infinity when it has an entry with a cost of 2? Well, it's because that update is coming from R3, which is R2's next hop. Right? So as soon as your neighbor says, you have a path through your neighbor and they tell you their cost has gone up, you have to accept that because that's newer information, that's better information, and what you have is outdated. And so that gets set to infinity. R2 is also going to tell R3 about its path through R3, saying it has a cost of infinity. And so very quickly, both entries are now no longer used. Does that make sense of how we get out of this scenario? I just want to really highlight, we're getting out of the scenario in the amount of time that it takes to send a new advertisement. We don't have to wait for anything to expire. So that's already an improvement on split horizon. So, to really concretely answer this question of what is this difference between poison reverse and split horizon, mechanically I've showed the difference. But intuitively, they should be preventing the same kinds of direct loops. They're both equally good at preventing. But in the case where we do get into a direct loop that they don't prevent, poison reverse squashes those loops much quicker than split horizon. Because you actively tell your neighbor through whom you're routing that you have a cost of infinity, so don't ever send me a packet to that destination. Yeah? No, I think when we actually implement this, if you have a cost of infinity, you don't send along that cost. But even if you did, I mean, the point is that if the destination is actually reachable, someone else's update will come in, and if anyone else has a path, it's going to be less than infinity, and so you're going to take the route through someone else. The problem is, while you still have your old update, I'll just point this out. This is a good question. While you are in this state, if someone else tells you, oh, I have a path to D with cost 6, you're not going to take it because you still think that R3 has a path with cost 2. So the quicker we can change that to say infinity, the quicker this router is able to accept updates from other neighbors. Yeah? One downside to split horizon is that to poison reverse is that it's chatty, right? It's going to send it's going to send this infinity instead of being quiet. But the difference is negligible in the amount of traffic we send. So no, I don't think I can think of a reason. Yeah. Any other questions? Okay. Cool. Okay, fun aside, Can anyone guess why it's called split horizon? I was able to find this kind of cool picture of an actual split horizon on Reddit. And Reddit has everything. Yeah? Okay. Yeah, so it's like by breaking a loop, you're having the two neighbors take other paths. That's a good guess. No, but I like that. Any other guesses? Yeah. It's what? Like a boundary between the two neighbors, they don't talk to each other? That's also a cool guess. No. Okay, I'll reveal it. I looked this up, and in the original paper, they describe like the forming of an update of like all the paths that you have is kind of your horizon. And I imagine it's like you're a node in the graph, and you look outwards, and I guess that's kind of like your horizon, like how you get to everywhere else. But specifically, it's split because you're omitting information to a particular neighbor. And so different neighbors are getting kind of different views of your horizon. Particularly, the neighbor through which you're going is getting you leave out the paths, the routes to destinations that you use that neighbor for. And so each neighbor is kind of getting a different overall view of your horizon. The paper also describes this term as a whole horizon, which is like without split horizon, if you're sending everything, it's called whole horizon. We don't use that in this class, but it's kind of cool. Okay, we've solved our looping problem. That's great. Yeah. It's a good question. Let's think through that. How would we go about implementing both split horizon and poison reverse? So what does split horizon say to do if you have a route through that neighbor? Don't say anything. What does poison reverse tell you to do if you have a route through that neighbor? Say something. You cannot do both, yes. Right, you can't both say nothing and say infinity. You have to do one or the other. Yeah? Yeah, we will. But this is as we're deriving kind of step by step as we get kind of cleaner and cleaner solutions. Okay. So let's deal with this last problem that we identified, stale network information. So how do we get into this state? Any change in the network state is going to be an issue for us, right? It takes time for this information to propagate through the network. And in particular, I'll point out that different classes of information take different amounts of time to propagate. And so these are terms that, I don't think Sylvia uses in this class. I just have painted it this way of kind of like additive information, like someone comes up. So information that you didn't have before, new information, versus subtractive information, meaning information that people had that now needs to be revised or removed. And specifically, additive information propagates as quickly as the advertisement frequency. And that's relatively short. We're going to be, because we want to resend updates, we're sending quite frequently, much quicker than the time to live. Subtractive information, so information gets removed as quickly as it can expire. And that's always longer than our advertisement frequency. And so in particular, we get this issue with information about a router crashing, or a link going down, or hosts being disconnected. Once someone has told you about this, that's not going to get removed from your table until it expires. So what can we do to improve this propagation time? So this is the separate kind of slightly orthogonal problem that route poisoning is trying to solve. And the key observation that we saw with poison reverse was you can override a neighbor's time to live, right, by sending an advertisement that has infinite cost. So rather than waiting for someone's information to expire, you can actively tell them, this information, this host still exists, but the cost is infinity to get to it through me. And And so we're going to take advantage of that to try to get to a place where we converge more quickly, where information